High in the mountains, fast-falling streams hold immense power. The Pelton wheel, built for high-pressure jets, transforms this force into smooth rotation, generating electricity for towns and industries through the precision of high-head hydropower. The story of the Pelton wheel begins in the late 19th century, during a period when water power was being transformed from simple mill wheels into sophisticated turbines. Lester Allen Pelton, an inventor from California, was observing the way water jets struck paddle wheels used in mining operations. He noticed something interesting: the existing wheels were not extracting the full energy from the water. The old paddle designs would let much of the water's force pass through unused. Pelton realized that if the shape of the buckets could split and reverse the direction of the water flow, nearly all of the kinetic energy could be captured. By experimenting, he developed a wheel with deep, double-cupped buckets that split the jet into two equal streams, each turning smoothly outwards. This meant the water transferred almost all of its energy before falling away at low speed, wasting almost nothing. The genius of the Pelton wheel lies in its simplicity. It is an impulse turbine, which means it extracts energy from the speed, not the pressure, of water. The water is first channeled through a nozzle, which converts pressure into a high-velocity jet. That jet strikes the buckets mounted around the edge of the wheel. Because the buckets are shaped to reverse the jet's direction, the maximum possible momentum is transferred to the wheel. This makes the Pelton wheel ideal for high-head applications, situations where water falls from great heights, sometimes hundreds of meters, before reaching the turbine. At such heights, water gains enormous potential energy, which is converted into speed as it travels down the penstock, the large pipe carrying it to the turbine. When you step inside a high-head hydropower plant using a Pelton wheel, the machinery looks different from low-head plants. Instead of large spiral casings and submerged runners, you see a polished metal wheel with buckets around its edge, positioned so that powerful jets of water strike it tangentially. Each bucket is like a precision sculpture, carefully shaped to split the incoming jet into two symmetrical streams, reducing splash and turbulence. The wheel itself can be vertical or horizontal, depending on the plant's design. For large installations, the wheel might be several meters in diameter, with dozens of buckets mounted around its rim. The nozzles feeding water to the wheel are equipped with needle valves that adjust the jet size, allowing operators to control the turbine's power output quickly and efficiently. The physics behind the Pelton wheel are as beautiful as its design. When a high-speed jet of water hits the split bucket, it changes direction by almost 180 degrees. This change in momentum produces a force that pushes the bucket, and the wheel it's attached to, forward. Because the water leaves the bucket at a much lower speed than it entered, nearly all of its energy is captured. Efficiency can exceed 90% when the wheel is operated at its optimal speed. One of the great advantages of the Pelton wheel is that it can handle very high heads, from about 150 meters up to more than 1,800 meters. This makes it the turbine of choice in mountainous regions such as the Alps, the Andes, the Himalayas, and the Sierra Nevada. Where rivers plunge through steep valleys, the Pelton wheel can turn even a relatively small flow of water into substantial amounts of electricity. The Pelton wheel also has an advantage when it comes to maintenance. Because the wheel operates in air, not submerged in water like reaction turbines, it is less affected by cavitation, the damaging formation of vapor bubbles caused by low pressure. This means less erosion on the buckets and a longer operational life. The main wear comes from abrasion if the water carries sediment, but in many high mountain sites, the water is naturally clean and clear. In plants where sediment is an issue, engineers install settling basins or desilting chambers before the penstock to remove particles that could damage the wheel. The buckets themselves are made from high-strength stainless steel or even coated with special materials to resist wear. Modern Pelton wheels are often paired with sophisticated control systems. Multiple nozzles can feed a single wheel, allowing the plant to operate efficiently at different loads. If electricity demand drops, some jets can be shut off entirely while others continue running at full speed, keeping efficiency high. The generator connected to the Pelton wheel is usually placed directly on the same shaft, converting the rotational energy into electricity through electromagnetic induction. In large plants, these generators can produce hundreds of megawatts. Smaller Pelton wheels are also used in micro-hydro installations, providing power to remote villages, mountain lodges, and mining camps far from the grid. Historically, the Pelton wheel played a key role in powering mining operations during the California Gold Rush. Its ability to produce large amounts of mechanical energy from high-head water sources made it perfect for driving rock crushers, or processing mills, and pumps. Over time, as electricity became the preferred way to transmit energy, Pelton wheels were connected to generators instead of mechanical equipment, paving the way for modern hydropower systems. From an engineering standpoint, the Pelton wheel's bucket geometry is critical. The double cup shape, with a sharp ridge down the middle, splits the incoming water jet into two equal streams. This symmetry ensures that the wheel remains balanced as it spins. The angle of the cups is designed so that the water exits at low velocity, nearly at rest relative to the wheel, maximizing the energy transfer. When operating at full load, the noise of a Pelton wheel is a distinctive roar, the sound of water jets hitting metal at incredible speed. Standing near a running Pelton turbine is a reminder of just how much power a mountain river can unleash when guided by human engineering, in modern hydropower. The Pelton wheel is often compared to other impulse turbines like the turbo wheel or cross-flow turbine. While these alternatives have their own advantages, especially at lower heads or varying flow rates, the Pelton remains unmatched in its efficiency for very high head, low flow situations. Another reason for its enduring popularity is scalability. Engineers can design Pelton wheels from small 1 kilowatt systems for off-grid cabins to massive multi-megawatt units for national grids. This versatility ensures that the Pelton wheel will remain relevant even as renewable energy systems diversify. Some of the world's most spectacular Pelton wheel installations are found in remote and dramatic landscapes. In Norway, high-head plants use water from mountain lakes to generate electricity in underground powerhouses hidden inside solid rock. In Nepal, Pelton turbines provide power to communities high in the Himalayas, where transporting fuel for generators would be nearly impossible. The environmental footprint of Pelton wheel plants is generally lower than that of large dams. Because they require a high head but relatively small flow, many Pelton installations are run-of-river schemes, which divert part of a river through a penstock and return it downstream without creating massive reservoirs. This can reduce habitat disruption and flooding of land. However, like all hydropower systems, they must be carefully designed to maintain river health, ensure fish passage, and respect local ecosystems. Modern designs incorporate measures to release environmental flows, ensuring that enough water stays in the natural channel to support aquatic life even when most of the river is diverted for power generation. Pelton wheels have also proven their worth in hybrid systems. In some remote areas, they are combined with solar power, wind power, and battery storage to create a reliable, year-round energy supply. In winter, when sunlight is limited but snowmelt-fed streams run strong, the Pelton turbine becomes the primary power source. In summer, it can supplement or balance variable solar and wind output. Even after more than a century since Lester Pelton's first invention, the core principles remain the same: harnessing the speed of water from great heights, splitting it efficiently, and converting that motion into useful energy. The materials, manufacturing techniques, and control systems have evolved. The elegance of the design remains unchanged. Conclusion: the Pelton wheel is more than just a turbine, it is a bridge between the raw, untamed power of mountain rivers and the structured, usable form of electricity that drives modern life. From its origins in the gold fields of California to its role in powering nations today, it stands as a testament to practical innovation. In the isolated valleys and high peaks of the world, Pelton wheels quietly spin, driven by streams that have flowed for millennia. They do not demand vast reservoirs or sprawling infrastructure. Instead, they make use of what the land naturally provides: height, flow, and gravity. As we look toward a future that demands cleaner, more sustainable energy, the Pelton wheel's ability to deliver high efficiency in challenging terrain will keep it in service for decades to come. Whether in a massive underground powerhouse or a small village microhydro system, the principle remains the same: let the mountain's water fall, guide it with precision, and turn it into light, heat, and life. In the rush of a high-pressure jet against polished steel, in the hum of a generator deep in a valley, we find a perfect partnership between nature's gift and human ingenuity. That is the legacy of the Pelton wheel, a legacy still spinning strong.